Hello everyone, this is video 11.4 and we're going to be looking at converting from one unit of measure to another. So it's a little bit of a misnomer because we're not just converting like one unit, but like one type of unit to another. So it's not just going to be like 1 meter into feet or 1 mile into kilometers, but just from one unit to another. Um, some of the conversion factors we're going to know, some of them we're not, but we'll look at it a little bit more specifically as we go. So let's get started. So the most basic sort of level of doing this is going to be solving something that I'm going to call a direct conversion. And what I mean by a direct conversion is we have the given amount, and we have a conversion factor that's in units that both we have and that we need. So, as an example, if we have 8 pounds, we want to find how many kilograms that would be. So, we have a problem that is in pounds and kilograms. And we're given a conversion factor that's in both pounds and kilograms. Now, your book makes a big deal about multiplying and dividing, and I don't know if that's really the best perspective to have on this, because really, if we just solve this as a proportion, then we have the same setup no matter what. We need to make sure that we are consistent, that if kilograms are in the numerator here, then the kilograms are the numerator here, and that if we have pounds in the denominator here, then pounds go in the denominator here. And so everything should align in that way. And then once the units are set, then we just solve the proportion. Effectively, the units cancel. If we were to multiply this over, then we have kilograms times pounds, and this would be kilograms pounds, and then they would effectively cancel. So this may be a little bit out of sync for some people, because if you haven't taken 137 yet and you haven't thought about solving proportions for a while, this may be a little bit harder for you than someone who has recently had 137 or done, taught or done proportions recently. I just as a quick uh, aside, I would just there's more to doing a proportion than just cross multiplying. So I'll just kind of leave it at that. But to me, this is the more universal way of solving this problem, just by setting it up as a proportion and then solving the proportion. Trying to find a way of, okay, when it's this you multiply, when it's this you divide. It's overcomplicating things. So just doing it as a proportion is a little bit more direct and simple. So most of the problems that you're going to see are going to be much more complicated than all of that. A lot of times we're going to be given a conversion factor that is not in the units that are of the amount given, and sometimes the conversion factor will not be in the units of the solution that you need to find, and a lot of times it won't be either. So I want to walk through kind of slowly a problem that is set up like that. So the question is, how many feet are in 3 meters? And then our conversion factor is inch to centimeters. So we know that 1 inch is 2.54 centimeters. So you can see, we're we want to find feet, and we have inches. We're given meters, and we know centimeters. So nothing really matches up. So this is about as long and complicated as it's going to be. So if you can understand how to do this problem, then you're good for the rest of this section. There's two really fundamental ideas that this uses, and the first one is that anytime we multiply by one, we keep the same value. We preserve value. If you've thought about, done, studied, taught, whatever recently fractions, then you know it's the same principle. If I want to change 1/2 into fourths, then I multiply by 2 over 2 and get 2/4. And the idea is that 2 over 2 is a 1. So anytime I multiply by 1, I keep the same value. This is the same as multiplying 1/2 times 1, which is 1/2. So multiplying by 1 keeps the same value. So I want to look for things to multiply by where the numerator and denominator are effectively the same. Now, in this fraction example, they're literally the same, and it's 2 over 2. But we're going to use these conversion factors because they're equal to create fractions that are equal to 1 that may not obviously look like they're equal to 1. And so we'll see what that looks like here in a moment. And then the other important idea is that the same unit in the numerator and the denominator will cancel. Um, so I'm working through the units, and the number is almost coincidental. The main thing is I want to make sure that the units end up the way I want the units to be, and then everything else will sort of follow from there. But if I have a unit in the numerator and the denominator, they'll cancel. If I have the same unit in the numerator and the numerator, then I get that unit squared, which a lot of times is not what I want, especially for the problems that we're going to be looking at. So units will only cancel if I have 1 in the numerator and 1 in the denominator. So let's go through the first step here. We're given 3 meters, and our conversion factor is in centimeters, so it makes the most sense that I want to get to centimeters. Now, I could make this a lot more complicated and go from meters to decimeters to centimeters. I don't know why I would necessarily want to do that. So I'm going to take really the shortest route here that's reasonable. Now, the conversion factor that we were given from inches to centimeters, I'm not going to expect everyone to memorize those conversion factors. That's not a really reasonable thing for me to expect people to remember. But you do need to know these prefixes, and you do need to know sort of the basic conversions. I'm going to expect everyone knows 12 inches and a foot. If you don't know 12 inches to a foot, then you need to know those. So these basic conversions within a system, so meters to centimeters or kilometers or whatever, and then inches to feet. Feet to miles is a little obscure, so I mean I might give you that one on a test. But it wouldn't hurt to know it. It's a good thing to know. 5280 feet to a mile. So these conversion factors like centimeters to meters, you pretty much need to know. Now most of the stuff that we're going to be doing, you'll have access to, but it's a good thing to know. So I want to get from meters into centimeters. With a lot of students, you may find it helpful to put this over 1 and make this a fraction. And the reason being, then this meter and this meter, these 2 units, are more obviously numerator and denominator, and then we can see that they'll cancel. If we don't put this first fraction over, or this first value over 1 and make it into a fraction, it might be a little harder for some students to see. They may only recognize numerator and denominator when it's explicitly a fraction, rather than just assuming that if there's not a denominator, then the denominator is 1, and so the value is in the implied numerator. So if students have a hard time seeing that this meters is in a numerator, then just put it over 1 and make it a fraction, and then it should be a lot more obvious. Now we're using rule 2 here. I got the same unit, numerator and denominator, so it cancels, and I'm only left with this unit, centimeters, which is the unit I wanted to end up with. So that works. The other principle that we talked about is that we're multiplying by a 1. And so we have here that 100 centimeters over 1 meter. Well, these are equal to each other. We know that 100 centimeters equals a meter. So if these 2 things are equal and I make a fraction out of them, then that equals 1. I have a fraction where the numerator and the denominator are equal, and that's a factor of 1. So it may not be as obvious for some students. You may want to write this fraction like this, 100 centimeters over 100 centimeters, and then they can explicitly see the numerator and denominator are the same. And so that's maybe more obviously a factor of 1 for some students. And then change this out and say, okay, well, 100 centimeters is the same thing as 1 meter. And so now if this equaled 1, then so does this. And you shouldn't have to do this too many times before students start to see, what's going on here and what the point is. But some students may benefit from seeing this explicit fraction, 100 centimeters over 100 centimeters, before we get into this like slight abstraction of this fraction. So we do the 5 meters times 100 centimeters over 1 meter. The meters cancel. 5 times 100 makes 500. And so I've converted successfully my 500 or my 5 meters into 500 centimeters. The next step is to actually use the conversion factor. And so now I'm going to be converting from centimeters to inches. A lot of what we've said in the previous slide applies. I can still put this over 1 if I need to. I got a centimeters in the numerator and 1 in the denominator, so they cancel. I want to end up in inches. Inches is in the numerator, which is what I want. These two things are equivalent, so I've got a factor of 1 here. I'm multiplying by 1 because 1 inch and 2.54 centimeters are equal, so that creates a factor of 1. So now I'm going to divide 500 by 2.54, and I get 19.86 centimeters approximately. There's some rounding in there. So that's approximately our solution. So now lastly, we need to convert this into our final units. So I'm going to take my 196.85 inches, and the same thing, I got inches here in the numerator, inches here in the denominator, so they cancel. I got feet in the numerator, which is what I want, so that's going to be my units at the end. Again, I can put this over 1 if I need to. So I got 196.85 divided by 12. Again, I'm rounding a little bit here. So that's an approximate. We're not going to sweat that too much. We talked about in the previous section, I got 2 decimal places from the start, so I'm keeping 2 decimal places as I work through the problem, so I know how much to round to. And again, this is a factor of 1 because 1 foot and 12 inches are equal. So I know that the numerator and denominator are equal, so this forms a factor of 1. So this would be my final answer. 16.40 feet. 3 meters would be about 16.5 feet, roughly. Now, I worked this through kind of step by step, and students may see the same problem written like this, where everything's sort of in one line of work, and then you can go through, we can see meters cancels, centimeters cancels, inches cancels, and so I get feet here at the end. This is all the same work from the 3 previous steps. You can see this is step 1, this is step 2, and this was step 3. So this is the same thing we did on the previous 3 slides, sort of condensed. A lot of books show it this way. You'll see students who they could do it 1 step at a time and get it correct, but if they try to write it all in 1 line like this, they get it incorrect. And one of the biggest confusing factors is here we've got the number that's not a 1 in the numerator, and here we've got the number that's not a 1 in the denominator. And so sometimes students will get a little confused by this and think it's always supposed to be 1 in the numerator, or it's always supposed to be 1 in the denominator, rather than looking at the units. The units are much more what sort of dictates what goes where. So if it's really confusing for students to do this way in this 1 line, just tell them not to do it. Or don't do it yourself in class, and don't model that. And then the students who are able to do it in 1 line, eventually they'll figure that out and they'll do it on their own. But there's no real benefit to doing it in 1 line like this. I mean, you could argue that it makes it a little bit quicker and a little bit faster. But I don't know, if you're doing it faster and getting it wrong, I don't know if it's really the better way to do it or not. So, be watching your students and really get a sense of how concretely they need to write this work out. A lot will need to, some won't, but just sort of gauge that with your students. So if we go back to section 11.1, we looked at how linear area and volume measurements changed a little bit. So let's look at this square here, and this square is 1 yard by 1 yard. So we could call this 1 square yard. But it's also, since 1 yard is 3 feet, we've got this is a foot, this is a foot, this is a foot, and these are feet here also. And so the question is 1 square yard equal to 3 square feet? Well, we've talked about this before, and you can see, if you don't recall, that no, 1, 2, 3, 4, 5, 6, 7, 8, 9, there are 9 square feet. Each one of these squares is 1 foot by 1 foot. You can see here that it's 1 foot by 1 foot. So we have 9 of these square feet. So 1 yard is 3 feet, but 1 square yard is 9 squared feet. So this is going to be really important for some of the problems we're going to be looking at, but let's look at how this relates to volume as well. So again, we looked at this in section 11.1, so as a little bit of a refresher, again, this is 1 yard by 1 yard by 1 yard, so this is a 1 yard cube. And so is this going to be 3 cubic feet? Well, we can see here's 1, 2, 3 cubic feet. So it's obviously more than that. And then we saw on the previous slide, this is 4, 5, 6, 7, 8, 9. So there's my 9 square yards as the surface area, but I've got this 9 3 times. So there's 9, 18, 27. So I can see this is 27 cubic feet. And so hopefully you've sort of picked up here that this 27, the units are being cubed, so is this conversion factor. So this is 3 to the third cubic feet. So not only are the units being cubed, but so is the amount. So this 3 times 3 times 3 makes 27. So how does that relate back to, like I said, the problems that we're looking at in this section? Well, if we look at the first problem that we talked about, we were given that 1 inch was 2.54 centimeters. So then if I wanted to do a problem involving square inches and square centimeters, then reasonably that 2.54 is going to change, and it does. As I go into square inches and square centimeters, this 2.54 gets squared and becomes 6.45. And if I move into cubic, if I move into volume, so this is for area here, and this is for volume here. So as I move into volume now, 1 cubic inch is going to be all of this cubed. So 2.54 to the third power is going to make 16.39, and you see here that I'm in cubic centimeters now. The previous slide I was using exponents. Here I'm using SQ and for square and CU for cubic, but it's the same thing. It's just a different way of writing it. So let's go through the first problem again, but use area instead of volume. So instead of solving for how many feet in 5 meters, I want to know how many square feet are in 5 square meters. And so the linear problem looked like this, but the area problem will look like this. And so you can see here the 5 stayed the same because this is what's given. So I don't need to square this 5 because I'm given the 5 square meters. So that's the only thing that's really going to remain constant. If you look at this conversion factor, I've got 100 centimeters to 1 meter, and now I've got 10,000 centimeters squared to 1 meter squared. Again, because I'm going from linear into area, this linear measure into area measure. So I need to think about, this one big square here that's 1 meter by 1 meter. So that's my 1 square meter. But if I also do it as 100 centimeters by 100 centimeters, which is the equivalent of 1 meter, then the area here is going to be 10,000 centimeters squared. So this conversion factor has to change also. If you need to draw these squares and think about what that conversion factor is going to look like and how that changes within a system, if that helps, by all means, draw those little squares. But a lot of times students will remember to change this conversion factor, but forget to change the conversion factors within the system, this metric conversion and then this U.S. customary conversion. The same thing's going to happen over here. 1 foot is 12 inches, so 1 square foot is going to be 12 squared square inches, or 144 square inches. And then the rest of it just solves out as normal. So 5 times the 10,000 makes 50,000, divide by 6.45, divide by 1.44, and then I get 53.83 square feet. So 2 things I want to point out about that solution that are really important. The linear solution is 16.4, so a lot of students, and you might even guess, well, if we're squaring everything, then we should just square the answer. And so if the linear solution was 16.4, then the area solution is probably going to be 16.4 squared. And that's not true. You can see we got a very different answer. 16.4 squared is 268, and we got a whole lot less than that. So the reasoning behind this, we don't necessarily need to get into the way some of these factors work. Not everything squared is if we square everything in the problem, it doesn't always lead to a squared answer. So it seems like that'd be the most reasonable guess, and of course, that doesn't work. Also, I wanted to point out that the conversion factors, they all need to be adjusted, not just the one that goes between systems, but the ones within the systems. And then also making sure that all of those conversion factors cancel as well. There's another way we could do it that we might talk about in class that might help some students, but I think it's typically more confusing. But all the units still need to convert need to cancel the way they did in the linear problem in the area problem. So square meters needs to cancel with square meters, square centimeters needs to cancel with square centimeters, and so on and so on and so on. So if you're a checkpoint problem, you can probably see where this is going. We've done 5 meters into feet. We've done 5 square meters into square feet. So now I want you to try to do 5 cubic meters into cubic feet. So we've walked through this problem a couple of times. You've seen it, and the conversion factor is in the slide. So most of the pieces that you need should be in there. So this should be solvable. But if you have any questions about this problem, how to solve this problem, or anything else from the slides or from the homework, as always, bring your questions to class and we will get them answered. All right, thanks.